All right, so today's presentation is going to be on attention network, but actually we thought about it, and if we just talk about attention network today, it will be missing out on a very general class of networks that is known as the augmented network, right? So the whole idea of augmented network is simply just to augment some kind of a structure to your network so that you create new properties for it, right? So we shall see more later, but let's start with the attention model first, all right? So let's start with some motivation for the attention model, okay? So if you look at this network, this is a standard machine translation network, right? So you have this encoder part right here, and then you have this decoder part right here, right? So what you're trying to do here is that you're encoding a sequence of words into one hidden representation right here, right? And this is quite a hard thing to do because you effectively trying to compress all the information down of your original sentence down into one hidden representation, right? So it might not be very effective. So what if we can do something like that, in the sense that we take all the hidden representations of the original input sequence, and then feed it into some kind of attention model and tell this attention model to say, okay, given a certain context, can we get, how much should we focus on some part of the hidden representation, right? So this is the big idea of an attention model. So how can we create such a model? It's actually quite simple. So let's look at some of the formalization, okay? So the inputs and outputs are quite simple. All this Y's, which is in our machine translation case, the hidden representations, which is this H. And we want to know how much of each of them to focus on, right? So hopefully what we can get out of this Z is a kind of a linear combinations of all these Y's, right? A weighted sum of all these Y's. And also, we want to have certain context C, which is to say, in the case of machine translation, so far we have translated this many words, and what should be the next word be, right? So this is kind of a context that you want to have to the attention model, okay? Mind you that this attention model is just one single model, so that's why we need to have the context, or it will always generate the same words, right? So let's look at this, right? So if you open up this attention model, you get something like that. Looks very complicated, but it's actually really, really simple. First, let's look at the inputs. So these are the Y's that we see just now, and the context that we have, right? So the whole idea is that given some context, you want to see how much of each of the Y is relevant to the context. So there are a few ways to do it. So one of the simplest ways, of course, is to take the dot product between these two, and we'll see that later. But in this case, they choose to use the 10H, right? So you just take a linear combination of the 10H, you train it on a certain weights, and you get some output M, right? So then after that, what you can do is you want to normalize this, right? You want to normalize this. You want to see which of these M's has the most significant value, right? So what you want to do is do a max operation to it. But again, if you do a max operation, you'll not be able to differentiate it. You can't backprop, so you do a soft max, right? So you do a soft max on this M's, and then you get some S1, S2, S3 up to Sn. And what you do after that is you take a linear combinations, you take a weighted sum of all the S's with your original Y's. So you can see that at the end of the day, what you have is a linear combinations of all the Y's, and that would be your Z, which is the thing that you want to attend to, right? A little motivation, like let me show you this animation right here. So on a high level, you can actually see that this is the attention. So how much should you attend to each of the words? Let's say if you are translating from English to French in this case, and we are looking at this word right here, right? You can actually see that if you want to translate this, if you want to get this la, we actually, is it la? How do you pronounce it in French? La, all right, yeah, okay. So you can actually see that we have a little bit of interactions with the and a little bit of interaction with Ariel, I'm not sure why it actually needs to get to the aerial part, but
Maybe because you have genders for each noun.
So
when depending like an area is feminine.
I see.
Anyway, it's related to,
All right.
to the next word.
I see.
It's a really good example because in English you wouldn't care, but in French you care.
Yeah. So in most romantic languages you have gender, right? So in German you even have neuter gender, but in English we don't have any distinction. So yeah. So that's why you need some attention on the noun to decide the gender of the determinant, right? In English, we have certain things that agree in number, like plurals and tense, but not in gender.
That's interesting. It's the 1992 thing, which you would, which is, okay, that's only 1992.
But what about the full stop? Why is it related to, you can't really see it here, but there's kind of a relation
to everything. I mean, it's kind of the end.
The end of the sentence, yeah. So maybe that it has to attend to whether all of the pieces of information have been said in the translation. So that needs some attention to all of those. You'll notice that all of the lines that are a little bit stronger are higher up in the sentence tree. So for example, the prepositional phrase is headed with in August 1992. So that's why we have to check whether that prepositional phrase has already been said in order to decide whether to end the sentence or not. Okay. Was signed is obviously is the head of the verb there, right? Okay.
All right. So this is another example that they give is on translation for the speech recognition. Yeah. So you can actually see that given a certain speech, this certain point of time, what should it be attending to, right? So like this is attending to this certain part, and then this wood, the wood of the wood is attending to this certain part, and so on and so forth. Okay, let's go back to the slides. All right. So any questions so far about the formalization of the attention model?
Just reading up that there's soft attention and hard attention. And so just to confirm, this is soft.
Yeah, this is soft attention. So what you do for hard attention is simply to replace this linear combination with a randomizer. So you put a randomizer here, and because what you get of all this S is some kind of a distribution of how much to choose from each of the Y1s to YNs, right? So the randomizer just sample from this distribution and give you one output. Yeah, so that is a hard attention. I think there is a result somewhere. Let me show you how.
The other window.
This.
And you choose the other window.
Where's the other window?
Go to Windows on the menu.
Oh.
Yeah, and then.
Oh right. Okay. Thanks.
Oh, you have to take it out from screen.
So there is.
A new link.
So I was wondering, when would anyone use the hard attention model versus a soft attention?
Like there will be an example for places where you want. Like I will talk about some cases where hard attention might make sense, even though I think they do soft attention for these cases. But yeah, just wait like 5 minutes.
Yep. So you can see actually these are the output of the hard and soft attention. So the top is the soft attention and the bottom is the hard attention. This is one of the examples that I'll give later. So I'll discuss more later. But you can actually see that the cell is actually the same. It's just changing this to random choice. Yeah. Most of the research is probably working towards the soft attention, because if you use hard attention, it's the same problem again. You cannot do backprop easily, so you cannot train this easily. Yeah, so that's that. All right. So if you modify it, the network that we see just now, this is how it will look like, right? So you have your input sequence, and for each of the hidden representation of each stage of the RNN here, you actually get this into the attention network. And then this attention network will now be able to weight how important each of this representation is and give you a linear combination of the hidden representation where the most heavily weighted one will be on the one that it should probably attend to, right? And then you get this as the hidden representation instead of the original big H to every single cell, right? So if you look at this diagram, you can actually see that you have all this S1, S2, up to Sn, right? So if we plot all this S1 to Sn, we can get a diagram that looks something like that, right? So you can actually then visualize how much each of the word has attend to with correlated with each other. So like I think you saw this just now. The lar is correlated to the aerial and der. Yeah, so that's that. Yeah, sorry.
Just and you can also see that like the order of the words is switched. So European and area. So the things which are not highlighted on that diagonal are not highlighted because actually the word order is switched in the French sentence. So zone is out of order. It's switched with European, and European, or how to say it in French, is switched is on the other side. So you have like this cross diagonal. Yeah, I'm going to do that.
Anyway, if you're interested in the paper, it's here. I think this one is on. Oh, I forget the title of the paper, but okay, great.
The question for this matrix, if you have a different number of words, does it also?
Sorry.
And you mean if the translation would have more words?
More or less. Yeah.
So these are very standard questions that we ask in machine translation. So fortunately, you guys have agreed that you want to know more about machine translation next week. So we'll cover it again there. But basically, yeah, in machine translation, you have this big rectangle, right, where we're trying to align words to their translation. So there's obviously the part that Martin pointed out that sometimes word order between different languages are different. Right, so French arguably has a better order than English, where you actually have to talk about the object first before you can modify it. In English, we modify things without even knowing what they are yet, and then we tell you what it is at the end, right? So that's just different style of language. But there are certainly a lot of cases where you have to generate extra words or use several words to generate one word, and in the I guess we call it the traditional machine translations. This is called word fertility, like how much one word generates more than one word in another language. So there's a number of basic probabilistic models. They're called the IBM translation models that were created by researchers in the IBM TJ Watson labs in the 1980s, which basically took machine translation research from 1980 until about 2010, which all uses a very well mathematically principled setup of 5 different machine translation models. So we can talk more about it next time. But basically, yes, it has this feature where it can generate more than one word, or sometimes words are dropped. Like there are plenty of things in English that are dropped that other languages actually have particles or elements for, right? So for those who are speakers of Chinese, for example, the word "de" doesn't translate just to one "de" in Chinese. You know, it depends on what type of thing you're modifying. You know, whether it's a flat, long object or a thin, pencil-like object or a big object or not, or an animate object or not. They have different classifiers for each type of "de's," right? So for a Chinese to learn English "de," it's like, oh, this is really easy. There's no problem with that, right? It's very simple.
Okay. So here's another application, which is image captioning. So the idea of image captioning is that you're given an input image and you want to output a caption for the image, right? So in this case, the network that they use is quite straightforward too. Yeah. So classically, what you can think about it without the attention is that you have this image and you go through some CNN layer and you get some hidden representation of that image, which let's denote as H. And then with this H, you do the same thing. You want to decode this hidden representations using an LSTM network, right? So in here, what I think what they do is instead of just having one hidden representation, what they do is they just split up the image into regions, and then they do CNN on each of these regions, and then get n different hidden representations, and then use this to feed it into the attention model, and then do the same thing for the decoder network part, right? So as a result, what you can see is they can actually highlight the relevant regions of what this word corresponds to on the image, right? So this is pretty cool. So as we said just now, this is the soft attention and this is the hard attention. See, the hard attention is really just highlighting one region of the image, right? Well, yeah, that's probably my part of the presentation.
Okay. Yeah. So,
any questions? Any questions?
okay. Yeah, so,
Questions and discussions? You guys have anything you want to talk about? We can come back to it later.
Yeah.
I think both of you can help to answer questions at the end when people.
So yeah, Jeremy actually spent most of the lecture talking about clustering algorithms for whatever reason, and since we wanted to talk about attention models, we are not we skipped that part. If you're interested in clustering algorithms, go to the class. We are going to talk using attention models, and basically the idea of attention. We want to present some more models that use attention to augment our RNNs. And it will repeat itself, but I want to highlight, because that's the main idea, that you use attention in order to overcome a discrete problem. You use attention to make it continuous. And then, because it's continuous, you can actually backpropagate and you can learn on it. Right? On a discrete problem, it's way harder to learn. And there are 3 examples for that. The first is a neural Turing machine. So researchers which like Turing machines, some had the idea it would be really great if a neural network can actually access memory and write and read from the memory. So the problem is writing and reading are really discrete tasks, meaning you want to have one specific cell, and then you to write to, and then you want to read from the specific cell, and that's very hard to learn. So our RNN, as our normal RNN, has the same cell going through over and over again, and in every step it can write something to the memory and it can read something from the memory. And the memory is, because we have neural networks, is vectors, which are saved. But in order to be able to write and read, we use attention and basically read all the memory all the time. We just read some memory more and some memory less. So we put attention to a certain type or certain cell. We put more attention, and that influences actually what we read most. And then we we just take the weighted sum from all memory, and that gives us a learnable way of reading, and writing to the memory is the same thing. We decide where to put the attention, where to put what we actually want to write. Mostly, we take the old memory and a linear combination and write and create our new memory. And so the neural networks or the RNN actually get memory, long-term memory. And here's this is even smaller than I thought it would be. We can just go to the original. Get me. Actually, we can just go down here. No, that's wrong. Yeah, it's the first one. Give me a second. I'm really not used to having a Mac. Yeah. So how can I get closer? Zoom. Ah, cool. So at every step, it has like a memory and it has a query, which you can funnily influence. And it bits a dot product. So basically it learns, okay, on which query I should put attention where. And then it uses a softmax because dot product can be arbitrarily large. So it normalizes this. And it uses, because it's an RNN, it of course uses the state from the last step and interpolates the attention it spends the last time and the attention it spends this time. I mean, your state before should influence what you do now. And of course, you can train how much what should count. Should you like focus more on the query or should you focus more on your actual state? And you interpolate that. And then you have a shift filter, which sounds super weird because I already mentioned that we use the attention from the previous step, but you actually want to kind of, in many cases, you want to have something like a continuity, so you want to move through your memory. That will make more sense when we go to the actual applications, but think about adding a series of numbers or repeat a series of numbers from the memory. So you memorize the set of numbers and now you want to give it out again. So you actually want to have learned something like, okay, every time like you go through your RNN, you want to move one cell further. So you have this shift filter, and you can also have it in a way that it shifts backward. So basically that's the attention the query gives, but actually I want to look one step ahead. So you learn this shifting. Again, all is like a weighted thing, so you are continuous, so you can learn it. It's not like go one step back because it's hard to learn. Then you sharpen it, so you want to be as discrete as possible. So you like use an extra function to actually put more weight on things which actually have that weight. And here would be an example where actually having hard attention might be good, but hard attention is hard to learn. Let's try to go back to the slides for now. That's the second part. Okay, so what can they do? The original paper managed to store long sequences in memory and loop over this memory. So it could like repeating stuff back from memory, and it could actually detect anagrams. I think you know like words which read backwards and frontwards the same, which is, I think, relatively hard for neural networks, right? Yeah, it's for original neural networks, it's a hard problem to detect in long anagram. And it could mimic a lookup table, and it could sort numbers, which is also quite impressive. Like things neural networks usually can't do. Of course, they are all things which are relatively easy given a normal programming language. What they couldn't do was adding numbers or multiplying numbers. But that actually, they happened, the extensions which came later called Neural GPU, which could do some arithmetic. Then there are some people who tried reinforcement learning instead of this differential learning. This, again, could help with the hard attention model, I think. And they like, with the same idea, they played around with a couple of things. So there were people who used neural random access machines to have like non-sequential access to the memory, which implemented stacks and queues in a differential model, and who implemented memory networks. Questions to neural Turing machines. It's as I read it.
What problems or practical problems have they been applied to?
I don't really think they are there yet to have really been applied to practice. Like it's all read mostly like a proof of concept, because everything they achieved so far can be achieved relatively easy with the normal program. So I think the point of this area, and also the next one, is mostly doing things with neural networks you usually couldn't do. And then if you like develop this, you can reach a point where you actually like, if you combine that with the normal abilities of neural networks, you end up with something better, I think. But so far, it's more like a proof of concept, I believe. Yeah, you see everything they can do. Every first year computer scientists with Java can do.
Right. Just introducing more non-determinism in it.
Yeah.
Right? Okay.
Yeah. I mean,
so
since
2 times 2 is usually 4, but once in a while, when you apply hard attention, maybe you get 3.
Yeah, they kind of make it more human. Like they tend to make errors from time to time, which I'm not sure if it's a good thing or not. Okay. The next idea is adaptive computation time.
Why don't we stop there for a second and think, okay, now that you've heard about neural Turing machines and you know about other sequential models like RNN and LSTM and GRUs, what types of features do each of these have that you think would be useful for solving certain types of sequential problems? And so how would you characterize the difference between an NTM and an LSTM, for example? Silence. All your neural Turing machines in your head are spinning wheels. Is there anything different about the architecture of the memory being used, or about the way the memories are updated? What's the memory capacity of an LSTM or GRU or any RNN? Does an RNN have memory? No, right? It has state, but no memory, right? You update the state sequentially when you're exposed to multiple observations. So there's no memory in an RNN, right? What about the LSTM GRU? Do those have memories? Yeah, they do. What form is their memory?
Fixed and they.
It's a single vector. What about this neural Turing machine?
It's an arbitrary amount of vectors, but you have to keep in mind that they write and read from all the memory in every step. So having like they are linear, they are not too scalable in their memory, but basically it's arbitrary. Especially they can forget parts of the memory and have other parts stay the same. So they have a more capacity to remember, and the way they forget is modeled differently. So a neural Turing machine forgets by writing new things to the memory, whereas the LSTM has like this forget gate, right, which is kind of makes you forget.
Mm-hmm. Yeah, you have a separate gate for forgetting in the LSTM. Okay, in the neural Turing machine, though, if you go back to the architecture slide a little bit, you'll see that it looks pretty much like an LSTM as what it actually gets from memory, right? But there's an abstraction layer over the neural Turing machine, right? Because you're using attention to then do a dot product between the attention and the actual memory to get out a single vector, right? So the single that you get, a vector that you get out of the neural Turing machine, it's equivalent in some ways to what an LSTM receives, right? It's just that, you know, behind the scenes of a neural Turing machine, there's this big bank of vectors, right? That's being arbitrarily written or writing to by some focused attention mechanism, right? So there's an extra layer of attention that's allowing you to access a much richer representation of memory. Okay, so great. It's more complicated. And of course, that means more parameters, which you should already be worried about, right? Okay. With more power comes more overfitting. Okay. So if you know that, then what do you think these neural Turing machines are better for compared to an LSTM? You can give the obvious answers like, wow, if I have like Google-sized terabyte, exo-sized data sets, then probably a neural Turing machine is better because I have more complexity in my modeling. Okay, which granted was probably true. No matter where you put attention on what and where and how, you know, probably you can get a more rich representation that will fit better. Okay, but intrinsically, are there tasks that you think a neural Turing machine would do better on than the LSTM just because of its architecture could not do? I don't have an answer for it, so that's why I'm throwing it to you. That's my job as a professor, is to ask you all the tough questions.
Like, I mean, since a vector is multidimensional, you can actually have like also in an LSTM more or less arbitrary amounts of memory, right?
Mm-hmm.
So I think there's no task which you can do with the one and not at all with the other. But I believe the task where you have to remember multiple things and just use them from time to time. I don't know, fill out a form, for example, where you have to put in your name, you read the name first, and then you have to put in the name in the top, and then at some later part, you have to put in the name again.
Aha, so that invokes another network architecture that we've learned, which we learned last week. What was that called? Memory networks, right? Yeah. So, okay, there's another complication there. A memory network, you also have memory, but it's, you know, you have several lines of memory, right? They're all stacked on top of each other. And the idea behind a memory network is that one layer of memory will help you do a task later on, right? So exactly as Martin was saying, you know, you fill out your name, but in order to remember something from what you just filled out, then it will help you fill out another part of the form or something like that, right? So we saw on these very simple tasks last week that, you know, you want to remember where John dropped the keys, and you have to remember who dropped the keys first, and then where they dropped them, and then which key did he forget on the table or whatever, right? So there's a multiple layers of questions that are being answered and asked, and each one is sort of is sequential. You can think RNN style encoding of the attention model. So let's be clear, the neural Turing machine is not doing that, right? It's not layering the memory in such a way that it's, you know, that one set of answers helps you depend on another set of answers. In fact, you could also marry the memory network with the neural Turing machine, right?
Yeah, I think that.
And probably you are.
I haven't read the paper, but this memory networks, I mean, it was referenced. It didn't cut down.
All right, so this architecture is basically changing how we represent the memory in any one state, right? So you have the LSTM, and you're saying, instead of just thinking about an LSTM creating a vector, I'm going to use attention on that vector, and that's going to admit the possibility of a much larger backstore of memory, which is an array of vectors, right? So what capacity does that give you? It doesn't give us this a memory network type of capacity, which is basically using an RNN over an RNN, right? So you have an LSTM, and you're saying there's several levels of these LSTMs that are attending to different parts of the question, right? So you guys, please weigh in. It's supposed to be a discussion.
Would it be useful in sequences where the context quickly changes instead of building upon each other? So let's say in a sentence, you would assume that it takes the next word takes the context of the previous word. But let's say the story is like, and she said, sweetly by, or like some bad word. And so the context suddenly changes from sweetly to, from a positive to negative context. And so like the memory networks, it would build upon each other and incorrectly incorrectly weigh in a positive context. Whereas because the NTMs read and write, they can edit better discard the wrong context.
What do you guys think? Is that true, what Gabriela said?
Like, first I wanted to mention that it's like, I think a problem is also very typical from like dealing with language, that like a single word flips the meaning entirely, and then you have it twice and then it flips it back, like, and that's, I think, very, very hard to deal with. And probably, I mean, in a memory network, you could have something like just count the number of negations and use that like as one part of your memory, and then just look up, okay, how often did the sentence actually get negated, and use that as an output. So
probably you have young cousins, nieces, or nephews who, when they first learn negation, they like to play games with you, like not like, right? Or not like. Okay, so do you want it or not? I don't know. I forgot already, right? So think about the obvious application areas. We've talked a lot about vision, right? What about sequential time series information, either stocks, audio, natural language, right? Or some of you are in the medical field, you can think about medical problems that are related to any of these. Would any of these types of networks be more useful for that?
vision as in a video? Or, I mean, Eric, like,
I was thinking, like, as she said, like, when the student change, like you said, so if you have a trend, but simply you have, I don't know, like a crisis or something, and it changed suddenly, maybe maybe the NTM can better take the change and continue on the other trend, or that's my.
I don't think anyone in this room particularly knows, but it's good to discuss, right? That's the whole point. We're not trying to find an answer. Well, we are too, but we're also trying to find the right questions to ask.
I got a feeling that no matter LSTM or actually LSTM, because the memory is just a vector, but if the vector is big enough, I think it should be capable enough to do whatever the scenarios so far we have talked about. It somehow depends on also your data set, whether you have high quality data, large amount of them. It all boils down to so-called machine learning is, the models are, you can approximate any function, right? But to be precisely approximate any function, you just need large amount of high quality. It's more important than some of these architecture stuff.
So we already know that, the representer theorem, the universal representer theorem, says that a neural network of only like 1 or 2 layers can represent any arbitrary function, right? Given enough training data. So that is part of the answer. But the second part of it is, when we engineer neural networks, we're trying to create architectures that have parameter sharing and weight tying in a logical fashion, so that we don't have to have such gigantic data, right? So you can say, all right, let us compare apples to apples. Let's compare an NTM with the same number of parameters as an LSTM. How would we do that? It means that your NTM would have to have much shorter vectors, for example. They couldn't be, X dimensional, where X would be 300, for example. Maybe it can only be 20 dimensional, okay? Because you've got, all these, you've got 20 by 20 vectors, right? So that's already 400. So if you compare an LSTM with a 400 dimensional vector compared to a neural Turing machine with 20 dimensional vectors, then which one was going to work better, right?
I'm not quite sure in LSTM how is always a complete vector used, or is there a mechanism to pick out parts of the vector?
Mm-hmm.
It's a question.
Yeah. So there is a sort of an attention mechanism in the LSTM already, right? When you look at the input gate and how it decides what things to input, what things to write, and what things to get, there's also this function that you have to multiply against a W matrix, right? To say which parts do you want to put in. So it has a somewhat of an attentional status to it. It's not labeled attention per se, right? It's just saying how much do I want to remember as compared to the previous state, and then I'm going to insert it in, right? There is a selection gate too, right? So there's both the dot product and a selection mechanism to say what from the current observations I want to remember, commit to memory, right? So I think they're very similar, and I think you guys can try to figure out where the differences are, why one architecture might be more superior to the other for certain tasks. That's not saying a lot yet. Yeah, go ahead,
One
Harika.
question I have is, I'm not sure this is very basic, but NTM, so basically it just reads and writes from this, there's a memory array of, if there's an array of memory, it basically just reads and writes from it. But in LSTMs, you have, dot products and stuff. Basically, there's some more. So in this case, the computation of memory is a bit lesser than LSTMs. I mean, so is one of them slower than the other? Definitely.
I have no idea.
What do you mean by slower?
Is NTM slower than?
NTM is faster going. So you compare NTM with the LSTM. There's a graph.
You want to share that on Slack?
I think because there's a like read and write happen to see which one is significantly faster than that.
But the read and writes can be carried out independently, right? When you read, you're reading from for the next state, right? From the diagram that was shown. You're writing, you're committing at this time step, and you're reading for the next time step. If I understood from your diagram.
Yeah.
It can be serial, it can be parallel, but even in this application, it could be serial also. Because the word context depends. If the word is repeated before.
Is the computation time so critical? I mean, in my experience, it's like the training time is the thing you care a bit about, because in the end, if you have the function and you can actually store it, the computation is not so heavy usually.
Usually they're just dot products. But the big thing is there's a lot of memory requirements. It's usually not the computation, it's the memory. Because you have to store all of the embeddings somewhere, you have to store all the matrices somewhere, and then you have to do all the dot products to aggregate them, right?
Okay.
Go ahead.
I have two more models. And the next one I know less about, and I think there are even less applications for, but I thought it's interesting. So it's about adaptive computation time. So it's an RNN, which can, for let's say a read operation, so one input, it can decide how often it's actually repeating itself. And it's basically the idea, if something is harder, you want to think more about it. So in this example, basically it makes like 4 loops through the RNN for the first input, for the second it makes 3 loops through the RNN, and for the third it only makes 1. So the motivation is think when you have to think, and if you don't have to think, take the time. It could also be related, actually, no, it can't. I wanted to say that you could use it to generate more output for a single input, like to produce multiple words for one word input, but actually in this architecture, it produces a single output. Now, this is all a bit complicated. We have better pictures. And this is one time step, and that's still really complicated. So we go even further. So this is basically just the input and the weighted output. So basically, for all time steps, it puts something out, puts it into the next computation step of the RNN, and then it creates a weighted output. And the adaptive part is actually the rest, because it has a stopping function. So at every time step, it's not just generating an output, but it also generates a probability, how much the RNN thinks it's done with the computation, and feeds that. And it's like, this is a value between 0 and 1, and you start with 1, and if you are below epsilon, you stop. And you just like keep subtracting. And this is again kind of a little bit related to the attention idea, that this is basically, if you run out of attention, you stop computing. And finally, since we have this epsilon here, so we don't stop by when we reach 0, we stop when we are smaller than epsilon. You have kind of a little bit of weight left, and you feed this left weight into the weight of the last output. Basically, you cut off and over amplify the last computation step. Clear so far? Makes a little bit of sense.
Is it that it says you may look at previous 3 words, or sometimes you may just need to look at previous 1 word? So this is
no. The thing is, here you only have 1 input. It's basically how long do you want to chew on this input? And I said, I really don't have I probably should have looked deeper into the paper. They probably have an application for that. It's like you get a house, you get like a number, and you do some computation, but you think you're not finished, so you use what you've computed and do more computation on it. So you don't have more input. You have always the same amount of input. Has anybody an idea where you could use that?
And the structure is still the same, right? Just that this input, if you find this useful, so this will be carried for the future computation. But if you find this is no longer useful, then it's cut it off. You don't use it for the future computation. But the weights, you basically tune the weights to make the weights so small.
Let me go back and clarify something. So you have basically 2 levels in this. So you have the normal RNN level, which is basically read something per time step and have a state. And then you have the lower level, which is basically don't read something or read the same thing, and do multiple time steps on that. So it is significantly different from what we had before. I just don't know what it's used for. Yeah, that was all. That's like, I mean, if we have time, we can look into the paper.
Yeah, I think Eugene put it to Slack, right?
Eugene, maybe like they mentioned. Otherwise, I would go to the last thing I wanted to talk about, which has obvious applications.
Okay.
So the last thing is a neural programmer, and that's basically you want to use a neural network to create a program. Yay! And it's a program which is not like a really complicated program. It's basically a set of operations, and an operation can use like the output of a previous operation, or operation which goes like 2 steps back. So you basically have a sequence of operations. And you would like neural networks basically to come up with the sequence of operations. And the neural programmer is a way to do that. And it uses attention. And basically, it says in every time step, you can do every computation. So think of an operation as like adding, subtracting, multiplying, but you use the RNN to decide on how much attention you put on these computations. So you say in the first time step, I'm mostly interested in operation 1. So you actually want to add something. And operation 2, you want to multiply something. But what you end up with is, yeah, okay, do 99% addition, but also do some multiplication. And then you use the outputs of these operations and put them together to compute the input in the next operation. Yeah, so here you use, again, if you would select a single operation, you would be discrete, and that's hard to train. So you use attention to be continuous to end up doing all the operations, but you're trainable. Yeah, and here's how you compute the output. You basically say, okay, what's the output of the operation, and you put them together. Yeah. So what can you do? So this was only the idea. What they did in the paper, they actually used that to answer queries on tables. So they didn't do like adding and subtracting, but there's a typo. So this shouldn't be times, it should be types. So there are multiple input types. In arithmetic, you only have like you only have numbers. You input a number, you get output a number. But of course, since the RNN actually just decides on the attention, the operation could be over anything. So the input could be a table, the output could be a single vector or a single column. And then of course you have to like take care that you combine the right things. So this could be like a column query, and then it puts out a column. And as long as these also put out columns, you can combine them. Makes somewhat sense, I hope.
Good so far, yeah.
And you also need to reference the input a little better. Saying I'm not sure what I'm saying. I have to look it up. Oops. We have our attention. Yeah, it's all from this really good, really long article. And I forgot the last thing. Preventing the new programmer needs.
Do not by pinching.
So the neo programmer needs to answer questions like how many cities have a population greater than, give them a table of cities to facilitate some operations out of the network to reference constant in the questions they are answering, or the names of columns. So basically, it can reference from from city to a city city column. Yeah, so it can refer I think that has not so much to do with the idea behind neural programming. It's just if you want to apply it to tables, you need to these references, so you actually can get from, oh, this is a city, I want to look up in the city column. If I get that correctly, I got it yesterday. Yeah, so that's the idea behind neural programming. And the nice thing about neural programming in this way is that so far, if you wanted to do programming with neural networks, you needed as training data correct programs. So basically, you fed program code into your neural network, and you were hoping that the network learns to program from that. Now you just need the question and the output, because you can actually, like the neural program can decide which operation to use. The bad part is you really do every operation each time step, and if you have like computational heavy operations in there and you don't use them, you have a huge overhead in computation time. Again, do you want to finish?
Okay. All right. So Well, so a conclusion for this whole presentation is that you can see that the base structure for most of this is just a simple RNN. And we are looking at different ways to augment the RNN so that it can do different functions, right? So that's what exactly the first point is trying to say, right? It improved the capability of RNN. So I guess for most of the machine of the deep learning community right now is that you have some kind of intuition of what you want to inject to your network, and you try to formalize them somehow by introducing weights here and there, and then hopefully let gradient descent do its learning, and it eventually emerge the property that you want. But I don't know, like this is what's going on. I don't know. Yeah, but yeah. What do you think about it?
What do you guys think about it? Those of you who are busy typing away on your computer, you guys have something else to say? Working hard on your project and poster, I think. Who is using RNN or time series information in their research? Yeah, Jeff was.
For steps, I'm working on text summarization.
Mm-hmm.
So it's also sequence to sequence. And they also augment it with other stuff, like a pointer generator network.
Mm-hmm. Yeah, I noticed folks at Stanford, Abigail is really interested in pointer networks.
Yeah, so like the people are following by.
Okay, yeah. This morning, those of you who came in a little early, I was talking with Agolo, which is a startup from Columbia University, my old research group, who does summarization research. So they're a startup. They told me they're working with 500,000 news articles per day, doing summarization over that. And they have an extractive algorithm, which basically selects sentences, and they have it in a neural style. But they have a lot of other old tools. They said they're still using Stanford's co-reference utilities, etc., to do some of their other work. So when you do summarization, you may know if you're picking out sentences from news articles, they contain a lot of disfluencies. Like they'll say the company said blah blah blah, but if that's the first sentence in your summary, that's pretty useless because you don't know which company you're talking about. So you have to do co-reference resolution to say, oh, the IBM was mentioned in the last sentence, so change the company to that IBM said. So things of that sort. And there's a lot of these types of things that are being done. And you may know that summarization is a really important application now because of the amount of data that people are generating in textual representations, but also because people are using it to make financial decisions, right? Yikes. Yeah. So automated traders, they have algorithms that execute on, let's say, outputs from summarization articles, as well as Bloomberg news feeds that runs summarization and sentiment analysis to do automated trading. So, a news article comes out, and then roughly about 300 milliseconds after it's published, there are trades actually made based on those articles already. So it's really out there, and hopefully you don't have any exposure to these unit trusts. Or maybe it's a good thing, I don't know. But one of the scary things is because so many firms are using them, they have the same potential as in Black Friday 2008, which is like all the automated trading algorithms all decide at the same time to dump a stock, and then the whole stock market gets wiped out, right? So yeah, it's important stuff. So thank you for studying it. Okay, so that's the end of our presentations today. Let's thank our speakers. Okay, so you guys have your hard work cut out for you. For those who still haven't updated their abstracted title, do that. Okay, because STEPS is next Wednesday night. We'll see you all Wednesday night. Joel is not here, but I guess if you send him your posters by in the general or direct message him, maybe he'll be able to help you print out the posters today. Okay? All right, see you all on Wednesday evening. I see big grins, which means I'm not done with my project yet. Okay, good. All right, see you.